and welcome to this video about magnetic force. In the video we're going to look at magnetic force and another right-hand rule, how charges move through a uniform magnetic field, how we calculate magnetic force, and galvanometers. So when a charge moves through a magnetic field, it's going to experience a force, and that force is going to be proportional to the charge times the velocity times the magnetic field itself. So when we rearrange that, we can write it in terms of the magnitude of the magnetic field, and we get this equation where B represents the magnitude of the magnetic field. This is the magnetic force on that charged particle that's moving through the field. Q is the magnitude of the charge, of that charge, and V represents the velocity or the speed of the charge without a direction. Force needs to be calculated in newtons, charge in coulombs, speed in meters per second, and magnetic field strength is in Tesla, represented with a capital T. So you can use your right hand once again to find out the direction of magnetic force on a positive charge. When you hold your hand out, make sure your thumb is pointing in the direction that positive charge is moving, and have your fingers line up in the direction of the magnetic field, and your palm will be facing the direction of the magnetic force. And in this case, the magnetic field is up in the field in the same plane as the paper. The velocity and the motion of the charged particle is moving in the plane of the paper to the right, and then the force would be coming straight at you out of the paper. Let's try an example together. Let's say we have an electron moving north at 4.5 times 10 to the fourth meters per second. It enters a 1.0 Tesla magnetic field pointed upward. What's the magnitude and direction of the force exerted on the electron? And what would be the force if the particle were a proton? I know the charge of an electron is negative 1.6 times 10 to the negative 19th coulomb. I'm given the speed of that electron, and I know the strength of the magnetic field. I'm going to use the formula we just learned. I'm going to plug the values into that equation and now solve for the magnetic force. So my magnetic force will equal 7.2 times 10 to the negative 15 newtons. And now I need to figure out what direction that would be. If the velocity is north, and I think about north as being horizontal and flat in the plane of this screen, if it's lying on the table or in the plane of a paper, I'm going to draw that right into this screen. And then I'm going to look at the magnetic field is pointing upward. So I'm going to pretend like this dot is the magnetic field, and that's coming straight at me. And I'm going to take my right hand, and I'm going to put my thumb, line it up along the direction of this green line, and my fingers will be coming straight out at me. And my palm then will be going this way. That's kind of a thick line. That represents the force if the particle were positive. Now, the particle is not positive. Therefore, the magnetic force for this electron is going to be the opposite of what it would be if it were positive, because it's negative. So the magnetic force for the electron is going to be going to the left or west, if we think about north, south, east, west being in the plane of this page. The second part of the question, what would be the force if the particle were a proton? Well, it would have the same magnitude, right here, 1.6 times 10 to the negative 19. So the same magnitude would be there, but it would be east instead of west. So the force on a particle that is a proton would be the same magnitude, only it will be going east, because our right-hand rule works for particles that have a positive charge. So one application for this idea, where we have electromagnets, would be those old television sets that nobody really has anymore, but they used to operate on the principle of two electromagnets, one here and one here, that deflect the beams of electrons. One of the electromagnets deflects the beam horizontally, and the other will deflect the beam vertically. And then the direction of the beam can be changed by changing the direction of the current in each of the electromagnets. And this way you get a picture on the screen. If the electromagnets did not deflect the beam of electrons, you would simply have one right in the middle bright beam of electrons, and you wouldn't have a nice picture. Now let's consider a positively charged particle moving through a uniform magnetic field. And remember, these X's represent our magnetic field, which is going away from us into the page. And if we look at this particle and it is moving in a direction that is perpendicular to that magnetic field, we can use our right-hand rule and see that the force, the magnetic force, is going to be exerted this direction, if its velocity is this way. As this particle moves, that is going to cause it to change its direction, and as it moves along this path, you can see that the force is always pointing toward a central location on this circular path. So one other way to look at it is that the magnetic force is a force that maintains circular motion and changes only the direction of V, but not its magnitude. And that is, again, when the charged particle is perpendicular to the uniform magnetic field. And that brings us to another fun equation. When we have a current-carrying conductor, in other words, a wire with current going through it, and it is perpendicular to some magnetic field. Here we have our magnetic field going into the page again, away from us. When those are perpendicular to each other, then this is an equation that we can use to find the magnitude of the magnetic force. It's simply equal to the magnitude of the magnetic field times the current times the length of the conductor that is within that magnetic field. So another way that we can apply our right-hand rule is to think about the current, in this case, as the velocity. So you can think about putting your thumb straight up this direction, point your fingers in toward this page, and your palm should be facing this direction. So the magnetic force is going to be perpendicular to the direction of the current. Now, kind of an interesting thing happens if we put two parallel conducting wires near each other. And let's say we have two of these wires, and we're using this idea of they are into the page. So this wire is coming toward us, and this wire, the current is coming toward us. They're coming, the wire current is coming at us in the same direction. If you use your right-hand rule, you will see that the force from this wire will be in this direction, the force from this wire will be in this direction, and they are going to actually be attracted to one another. If two currents are in the opposite direction to each other, and we have this one going away from us and this one coming toward us, you can see then, use the right-hand rule to see where the force will be, and it will be going into the opposite directions. In other words, these will be repulsed by each other. That will be a repulsive force between these. Let's do a problem together. Let's say we have a 4.5 meter wire carrying a current of 12.5 amps from north to south. The magnetic force on the wire due to a uniform magnetic field is this many newtons downward. What is the magnitude and direction of the magnetic field? First, let's write what we know. I know my length, and it is in meters. My current is represented in amps. I'm given my magnetic force on the wire as 1.1 times 10 to the third newtons. And I'm asked to find the magnitude and direction of the magnetic field. So let's find the magnitude first. I'm going to use our equation. Magnetic force equals the strength of the magnetic field times current times the length of the wire. I'm going to plug values into my equation and solve for B, the magnetic field strength. And I get 2.0 times 10 to the first Tesla. It's actually 20, but I need to have two significant figures, so I can express this in scientific notation so that I can show that I indeed have two sig figs. Now I need to find the direction of that magnetic field. My current is going from north to south, so I'm going to represent north, south, east, west as being in the plane of this screen, or in the plane of your paper. Now, where is the magnetic force? The magnetic force is downward. So I'm going to draw an X to represent that it is going down toward the floor here, if I'm looking at things in that orientation. Now, when I put my hand on this page or on this screen, as long as your screen is lying flat, put your thumb aligned with this in this direction and the palm of your hand straight down, because that's the direction of the force. Which direction are your fingers pointing? They should be pointing in this direction. That would be the direction of the magnetic field. And as we've defined it, then that would be west. So, how do loudspeakers use magnetic force to produce sound? A loudspeaker is set up with a permanent magnet and a paper cone, a flexible paper cone that acts as the speaker, and it also has a coil of wire and that is wrapped around, attached to that speaker. When we have a sound signal that's converted to a varying electrical signal and it's sent along to this coil, that current causes a magnetic force to act on the coil, and then when the current reverses direction, that magnetic force on the coil reverses direction as well, and the cone accelerates in the opposite direction. That alternating force on the coil is going to result in vibrations of the attached cone. That produces variation in the density of the air in front of it, and in that way the electrical signal is converted to a sound wave that will fairly closely resemble the sound wave produced by the source. And last, let's take a quick look at what a galvanometer is. It's simply a device that uses an electromagnet as well as a spring. The current in a galvanometer enters that electromagnetic coil, and it's mounted so that it can freely rotate within that magnetic field that's being provided by the permanent magnet. The magnetic force from that permanent magnet causes the coil to twist, and the larger the current, the greater the torque, and the more the coil is going to rotate before the spring that's attached is going to tighten enough to stop the movement. The needle is going to deflect in an amount that is proportional to the amount of current in the coil. So a galvanometer can be calibrated, and it can be used to measure things like the gas gauge in your car is one example of a galvanometer being used. Ammeters that measure current are galvanometers, and so are voltmeters, which measure potential difference. Here are a few advanced ideas. Can you create an electromagnet that will pick up paper clips? Can you adjust the strength of it in order to pick up more or fewer? Try adjusting at least two different factors that might affect the strength of your electromagnet. Or do you have other ideas? Be creative, and I look forward to seeing what you come up with, and we'll see you in class.